Good afternoon. This is the second talk on stratified and non-stationary turbulence. So basically focus will be on measurements in theory, in particular parameterization of turbulent fluxes, and we will consider cases from free convection to very stable stratification. First, we all live in boundary layer. We spend our lives in boundary layer, and this boundary layer is turbulent. So it's very important for human society to know what is going on in these boundary layers for different problems like air quality or renewable energy, weather forecast, climate. So all things we are doing here, this community, it's very important for all mankind. So I'm happy our science is important because we humans live in turbulent atmosphere. So, and we people want to predict, we want to know what will be tomorrow or in several months or several years, and what's going on, how to predict. It's models. We all run models. It's a relatively new things, but it's developing, and all models, it's numerical models, and there is a resolution in these models. And maybe with exception of direct numerical simulations, all models require parameterization of subgrid turbulence. Subgrid turbulence we parameterize using different approaches. So turbulent fluxes, momentum, sensible heat flux, and latent heat flux or water vapor flux. Almost all models except DNS use for parameterizations Monod-Nabokov similarity theory and or bulk algorithm. So bulk algorithm, it's difficult to measure and to know fluxes, but we measure traditionally temperature, wind speed, humidity, and we can find turbulent fluxes using simple standard meteorological information. But it includes direct coefficient, Stanton number, and Dalton number, which actually you used for neutral conditions and adjusted with functions, similarity functions. This is integral functions psi, which relates later with phi functions, and through Monod-Nabokov theory. Already many times Monod-Nabokov theory mentioned here. It was derived originally by Obukov. Obukov length in 1946. Actually, paper was written in 43, but published 3 years later after World War II. And Monod was a student of Obukov. Derived this theory in similarity terms. But actually, all things was in Obukov paper. It was translated by Dusinger and Yeglom in published in Boundary Meteorology. Obukov paper is based on mixing length theory, and Monod-Nabokov is formulation on similarity. And they propose similarity functions, which is function of z divided by L. One aspect that I'd like to mention, my My master diploma is signed by Monin, my PhD diploma signed by WoAT. So it's not, I'm not kidding. So maybe it's the reason why I'm in this field and working with Monin of theory. So I collected both signatures.
When was this?
What?
When was this?
Master in Monin?
No, when did they sign you?
Master in 1980. And PhD in 1984. Monin similarity was formulated as surface scaling, and later Franz Newson proposed local scaling that actually we use because we don't measure fluxes on the surface, we measure fluxes on some height. And Sorbian, the big Sorbian, approximately in the same time argued that universal functions will be same as for local scaling, same as in surface scaling, the original Monin-local theory. It should be noted that Monin-local theory actually may be formulated in terms of similarity, maybe formulated in different scaling systems. So it's original. So Monin-local based on magnetic flux or U star, sensible heat flux, or actually it's buoyancy flux, buoyancy parameter, and it's maybe great length, scale, velocity scale, and temperature scale. Smith et al. Proposed same things, but U star is replaced by sigma W, and they derived similar things like in original Monin-local. Big Sorbian proposed so-called gradient-based scaling for stable stratification, and he argued that Richardson number is more convenient than the OL for stable stratifications, but it's still same approach. I also had exercised and derived similarity based on Doherty Razvidov scaling or just using Razvidov length. It's based on Brunt-Vesela and frequency and epsilon dissipation rates. So based on these three parameters, there is Razvidov or Doherty Razvidov length scale, velocity, and temperature. You can also derive similar things, for example, based on Bolzano length scale, but it's all Monin-local. Based on Monin-local theory, based on Kansas data, Buessener and Dyer proposed formulation for 5 functions, which is very popular for parameterization, and it's used in many models traditionally. It's very simple. It's for convective case, and this is on the stable case. But in stable case, similar or before, maybe Dyer proposed by, as mentioned today, Thomas, for Chankas and Zelitinkiewicz, this formulation linear equations. We had a special issue, 50 years of boundary meteorology, and John Garrett was lead author on top-sided boundary layer papers, and also several people from here, Matthias, Thomas, they are also authors of this paper. And I reviewed paper Dyer for Buessener-Dyer parameterization, and the question was, why is Dyer is so popular and highly cited paper in this topic. My quick answer will it just happened because in the right time, in the right place. But there is more long answer. First, because flux profile relationship very popular. Second, Disch-Jordan use physical. It's not just empirical equation based. We use physical principle like mixing length and ZLS scaling. Coefficient we use for carbon running turbulent number 1 and coefficient in formula 5, which is inverse critical Richardson number. And of course, its influence of Disch-Jordan is entirely important. In convective condition, but there are some two problems with Disch-Jordan. First, it's in convection conditions we have no -1/3 correct limit. Grachev proposed for core above algorithm blend Kansas and free convection formula, which for near neutral conditions it's close to Kansas. Kansas it's Disch-Jordan, Kansas or Disch-Jordan. And on free convection limits have -1/3. It's this scheme used in current Worf model. Also, it's used in core flux algorithm and for stable boundary layer Worf it's used changing precise results. Another problem with Disch-Jordan it's for stable certification. It's not follow. It predicts ZLS correct limit, but data show it's increasing slower than predicted by Disch-Jordan. In this one, you can see, and as I recall, Matthias also write some paper on this stuff, show that it's not consistent with ZLS. And we propose such things to save ZLS concept, and we say that monomorph theory for stable certification has limit of applicability. And functions, all functions, universal functions, depends on ZOL. But limit is described by Richardson number gradient and flux Richardson number. And if we limit by 0.2, 5m and 5h will be more or less follow 0. So this is subcritical, this is supercritical. But in this case, we have only several ZOL less than 10, maybe 5 maximum. But in real life and real for parameterization, we need all. For this reason, we use parameterizations for 100. We propose parameterizations for Shipa data and compare with different parameterizations, including Belcher's Holzler, chamber size, and this parameterization for certification used in Andrey's Shipa algorithm, and recently group from Alfred Wegener group derived non-iterative parameterizations for Arctic ice for some European climate and prediction models. Several words about Gastinis assumption for flux parameterizations. For wind speed 0, original flux parameterization gives 0. To avoid 0 fluxes, condition surface fluxes, proposed wind speed vector average wind speed replaced by scalar wind speed. Originally, it was proposed by Mark and Sam in '95. So it's include variances for horizontal velocities. In convective boundary layer, historically it was this term was characterized by Godfrey Villiers and Peters in '95, and currently included in Bora flux organisms like Rees-Ferrer and current WoAT models. So Godfrey and Villiers proposed characterization Cassini's velocity by Hilbert velocity scales. Equivalent level of progress for development of simple characterizations for Cassini stable boundary layer has not been done. So it's maybe considered in terms of Ivana as remaining changes for our science. That was simple characterization from Andrey's group. They proposed 0.5 meter per second for zero widths. Larry Mark proposed including mesoscale, but there is no mesoscale characterizations. So there is no simple parameterization like in convective, so it's maybe considered as a main challenge particular problem. In this case, it should be said that in convective and in stable stratification, characterization for Cassini is the same because we replace vector average mean speed by scalar average mean speed. One thing what I would like also to say, and there is some similar things which Ivan reported today. So this is universal functions, sigma W. I believe this is for sigma epsilon, 5m and 5h for convective and stable conditions for coastal zone for different big directions, onshore and offshore. It should be said that sigma W, similar to Ivan words, it's more or less follow, especially from winds from sea in coastal zone. It's follow to monopolar and different levels collapse very well in single curve. Also not bad for direction from wind speed for 5 epsilon, but case for 5m and 5h, it's worse or it's not working because it's counter cases, so fluxes and gradients have different signs. What is important that in the same case for the same data set, we may say that the monomorphic works more or less good for sigma W, especially for sigma W, but completely doesn't work for flux gradient parameterizations. Because we're out of time, so last slide. What is the most important achievements in the past 100 years? Of course, understanding atmospheric turbulence, different theory, concept, approaches, but we told enough, especially Thomas talk and Alexander. I will surprise you. I will say one of the more important achievements in the past 100 years for atmospheric turbulence is sonic anemometer. What is sonic anemometer? What is atmospheric turbulence? It's sonic anemometers. Of course, it's important other fast response sensors like gas analyzer, like sodas, etc. But without sonic anemometers, it was impossible to measure turbulence itself. And just imagine how many papers written and how many dissertations were defended based on sonic anemometer data. Sonic anemometer change. Second, I will also surprise you for atmospheric software and computing. If you look on old data, for example, Kansas, or people like Thomas, we remember we used papers, grid papers, pencil, and we had several points. And plots like Ivana showed today, where clouds and sorting data in different cases was impossible. So not only sonic anemometer, it's software and computers. Small computers on labs, it's allowed to do many things. It's also important computers not for data analysis and processing, but also for numerical modeling.
Machine learning now.
What?
Machine learning could be also included.
Yeah, yeah. So, in my opinion, sonic anemometer is like invention of 4T car. We currently drive car, but before it was horse. So, sonic anemometer are one of the important. And when Thomas, he reviewed first papers, first people, Abshuverov in Moscow and Kaimov who invented first sonic anemometers. And it's interesting historically, people, originally people don't believe that we measure with speed U prime, W prime, it will be stress on the surface. And it was in comparison in Australia, and Australia used like piece of grass on the scales, and it was wind and measurements from scales were compared with sonic anemometer. Say, okay, sonic anemometer work. Yeah, so it's surface stress on the surface, momentum flux, surface on the stress on the surface. Major remaining challenging. I'm happy that Ivana show these results because I also in the bank say that morning have its special case, and we should move to multi-parametric formulation of flux gradient and flux variance relationship, where classic morning case is just special case. I mentioned additional influence, it's maybe Coriolis parameter like in Sergei's formula, boundary layer depth, net radiation, upbeat phase, and other things. And today I know it's anisotropic. So this is pi theory, and pi 1 it's, let's say pi is here, for example, 5m, 5h, pi 1 it's 0 by L, morning over, pi 2 is maybe 0 by H, or in one case it's anisotropy parameter. So it's in line as today talks. And previously I also mentioned parameterization of Castiglioni's phenomenon for very stable conditions for light winds and stable, and it's also correlates independently what goes there in similar slide, last slide. Another things what I would like to say, I personally would like to see a long-term turbulent flux measurements like months, year, because we say we observe trend in temperature, we observe trend in other things in the climate system. But if we can plot long-term year or several years, seasons in turbulent fluxes and surface energy budget component, I mean including radiation and soil fluxes, so we all small-scale people, right? Atmospheric turbulence, and we should move to large-scale, climate-scale processes. Because if you say climate changing, but climate it's usually related with surface energy budget on the surface, so it should be trend in the if temperature increases, it should be trend in surface energy budget. Or in surface budget energy preference. And last point, I will disappoint you. So I believe our science, our field, maybe not all, but big part will call in the future meteorological engineering. It's same philosophy like for different sciences. In university we have civil engineering, chemical engineering, electrical engineering, aerospace engineering. I believe it should be a similar path for our science, like our chemistry and electricity. It will be engineering, meteorology. In the past, we work with, for example, we people Maxwell equation in heavy side formulation, but now it's in electrical engineering. And meteorological engineering, we will have tools. We will have tools and use these tools in engineering method for different problems for mankind. Something like that. Thank you.